In this lot, we talk about recursive. Here we see a recursive figure. We have an original picture. The figure here is the same with the original picture, but smaller. And then. This is the combination of mathematics and computer science. Very beautiful. Sometimes it's difficult to define an object explicitly. However, it might be easy to define this object in terms of itself. We can define the figure by the figure in smaller. We can define many kinds of objects, for example, sequence, function, algorithm, etc. In the definition of a recursion, we have the basic step and the recursive step. The smallest figure corresponds to the basic step, recursive step, and change the problem into the smaller, and so on. So we go to the last step. In the last step, we have the basic step. So for example, we want to define a sequence. This is the initial term corresponding to the basic step. This is the first one of the definition. The recursive step. So how to determine the term by some previous term. So for example here, edge of 1 is 2 times of edge of 0 plus 3. Because f0 is 3, so we have 3 and then plus 3. Here, 2 plus f2 plus 3 mean. And here we have 21. Well, we have to multiply the previous term, 21 and plus 3, we have 45. And this is the second, and we can define the sequence here by the recursion. Some example. We want to give a recursive definition of a power of n. Traditional definition: a multiply a multiply a. We have n time multiplication. The basic step means the smallest value of n. Because n is a non-negative integer, so the smallest is 0. And in the basic step, a power of 0 equal to 1. The recursive step, we want to compute the value of a power of n based on the previous. We can take the multiplication of in n minus 1 time. We multiply with a. Here means a power of n minus 1. And here we multiply with a. So it is the recursive step. From the definition here, we can write the algorithm to compute h power of n. In Java, calculate stated a power double a and n. The result is a double. It's often in the first line we write the basic step. In the case of n is 0, we return 1. In the recursive step, we call the power itself by n minus 1. After we have the result, we multiply with a. So for demo, we can out the power of 2 by 5 times. We call the power 2 5. So here if we run 32. Okay. Now we want to give a recursive algorithm for computing the critical common divisor. We have the theorem GCD of A and B, mean GCD of B and the remainder A modulo B. In the case B is not 0. So if B is 0, the result is A. GCD of 2 integers A and B. So the basic step in the case of if B is 0, the GCD is A, and the recursive step we reduce the problem in smaller GCD of B and A modulo B. So we can show here GCD of 24, 86. We call the GCD of 24 and 60. Stated. If we run, we have the GCD of 24 and 16 is 8. So did you remember? Maybe we can write the process in a lot manner. So in this talk, we focus on recursion. So if we come here, the GCD of 24 and 16, the problem reduced to the smaller problem 16 and 8. And here we call the smaller 8 and 0. This is in the basis that the result here is 8. We return the value here is 8. And we return this is 8. We can draw a bit of here is GCD of 8. In the bigger, we have the rectangle here. And this is the original rectangle. We can see the beta of recursion similar to the bigger here. So for the next, can you write the recursive definition for computing the factorial of n? We have the definition n factorial. We want to find a recursive definition. We focus on here. This is the product of the integer from 1 to n minus 1. By the definition, this is n minus 1 factorial. The recursion is that n minus 1 factorial multiplied with n. For the case of n is greater than 0. In the case n is 0, the basis step is 1. So we can write here, calculate factor n if n is 0, we return 1. In the recursive step, we call the factor by n minus 1. We get the result and we multiply with n. We want to compute the 4 factorial. So here we have factor 4. We have the factor for 24. The question here is how to execute the recursion in computer. We count with 4 because n not 0. We turn to here. We have a trick. We count the function itself. The count here is 4, n is 3. Because n is not 0, so here 2, and we try to count the function with the value of 2, and so on. We count to the basis step. So here we count 4 factor. The 4 factor count the 3 factor, and so on. In the last count, we make the basis step. Basis step here we return the value 1. We count the factorial of 3, and then we have to multiply with 4. And here we push the operator into the stack. To execute the recursion function in computer, we use a stack. In the task one, we count 2 factorial. In here, we push the multiplication with 3 into the stack. In the next count, we push the multiplication 2 into the stack. 4, 3, and 2. So in the last count, we count 0 factorial. Before we count, we push the multiplication into the stack. The result is here 1. Here we pop an element in the top of the stack. We have to multiply the result with 1. The result here is 1. It means the result of the recursion here is 1. The result of one factor is 1. Back to the previous count. In here is 1, and we pop the top of the stack was 2. The result here is 2. We turn back. If we pop the start here, and we multiply with 3, and the result is 6. And the last step, the step contains only the multiplication with 4. We turn in here, result is 24. In the previous, we have a linear recursion. We count in a linear manner. To compute the modulo exponent, did you remember A and B modulo M is A modulo M, and then we multiply B modulo M, and in the last we modulo M. We apply the theorem to compute the modular exponent here. So we can write this is the recursive step. In the case n is greater than 0, but if n is 0, we have b power of 0 modulo m. It means 1 modulo m is 1. So here, let a modulo exponent. We have b, have n, and using the recursion in this line, if n is 0, the result is 1. Here we call modulo exponent b n minus 1, and then multiply with b modulo m. And in the last, we take the result modulo m. For example, 3, 6 for 4, modulo 6 for 5. So we can run the remainder 36. Okay, this is the linear recursion, but we can do a binary recursion. We can split here. For example, 88, 2, and B is 44, because 88 is 2 multiply 44. But we can also split for 22. So here, if n is even, b n divide 2 modulo m, and then b n divide 2 modulo m, and in the last, have 2 modulo m. If n is odd, we have b n divide 2, the floor modulo m, and then b n divide 2, the floor modulo m. Here, modulo m. Here is just b 2 times of the floor of n divide 2 modulo m. Because we have n is 2 floor of n divide 2 plus 1. So here the rest is b modulo m. And here we take the result modulo m. In linear shape, from n down to 0, we have n step. But in the binary recursion here, we have b of n split into b n divide 2. In the second branch, b n divide 2. But the second branch is the same of the first. So we need to execute in the first. We eliminate the second branch because the value of the second branch is the same of the first branch. We need one step here to convert from n to n divide 2. The next we have b n divide 4. Divide 4 means divide 2 power of 2. N divide 2 means n divide 2 power of 1. We next. Before the last step, we have base of 1. So base of 1 means base of n divide 2 power of logarithm 2 of n. bn divide 2, bn divide 2 power of 2. The last, we have n divide 2 power of logarithm 2 of n. So how many steps we need? You see here for the root. So I think the step here is logarithm 2 of n. To conclude here, in the linear recursion here, we have the complexity of ON. But if we choose the binary recursion, we have O logarithm to N. A modulo exponent binary. The basis step is the same. If N is even, we have a modulo P and divisor. We do not count 2 times, we just count 1 time. If we count the first branch, we have T. So we have a T multiply T modulo F. L, and because N is integer, 2 is integer, so the result is integer. This is the first line. We multiply with T modulo N. Finally, we modulo the result with F. For here, run the same result. But we consider here some binary recursion. For example, here we have a Fibonacci number. The term is the sum of 2 previous terms. F0 is 0, F1 is 1. In the recursive step, Fn is the sum of Fn minus 1 plus Fn minus 2. For the case n greater than 1, this is the basis step. So now I want to execute the function. Here we have in Java fiber in n. If n is 0 or if n is 1, we have the basis step with the value of 1. In the recursive step, we return the fiber of n minus 1 plus with the fiber of n minus 2. So we have here a binary recursion, because to compute the fiber n, we have to compute 2 fiber. So we have 2 branch in a tree diagram describe the execution. So here we want to find the Fibonacci of 4. So we count here 3 and we count here 2. Before we count this recursion here, we have to push the rest. The rest is the addition and the count with n minus 2. We push the rest into stack. If we are in here, the stack is plus with F2. And the next with F2, we have to push the addition with F of 1 into the stack. If we are in here, we have the stack with addition with F0. So we made the basis step here. So the result is 1. After we finish function here, we pop the stack. So in this here, we turn to the second branch here. We want to find the value of F0. The result is 0. And then we have here the addition 1 and 0. It means F2 is 1. In the top of the stack we have here. So we count the branch F of 1. And then we plus. Similar, we have F3 is 2. And the last we take here. Here we count, and this here we have a 1. This here we have a 0. And we plus. So the triangle is 1. So we have a final result 3. So some Fibonacci number have to be evaluated double. In this triangle, we compute F1. But in the different branch of the recursion, we can see here this is F of 2. Here we have to evaluate the F of 2 once again. You can see F of 1. So F of 1 here, F of 1 here. We have to compute F of 1 3 times. Mean the duplication. So I can show here another symbol. We want to find the number of k combinator from the set of n plus 1 element. From the set of A elements, we want to take 3 combinator. We don't worry about order. It means 1, 2, 3 is equal to 1, 3, 2. It is the same. We count only one time. Don't worry about the order. C, A, 3. Did you remember the formula? This is the explicit formula. Here, we want to find a QC formula. If we have 1, 2, n plus 1 element in the set S, we have 2 ways. In the first way, we delete the n plus 1 element. So we have only n element from 1 up to n. We need to choose k element. So by the first way, the number is C and k. We always get the n plus 1 element. So here we have to choose k minus 1 element from the S and dot. Cn k minus 1. So this is the total number. If we don't know the explicit formula, we can use the thinking recursive tool to find the result.